today we're going to talk about vulnerable code, and I will present you why a vulnerability database should not be about vulnerabilities. So, quick word about me. I'm the maintainer of vulnerable code and scan code and other about code open source projects. I'm co-creator of package URLs, co-founder of SPDX. We had claim to fame. I signed off on one of the largest deletion of code commands in the Linux kernel. And trust me, I'm very good at deleting code. It's a skill. And believe it or not, we managed to actually trash and crash the build of the kernel just by deleting code commands and changing some command style. I'm also co-founder of CTO of Nextbee, which is the maker of Deja Code. Okay, agenda today. We're going to talk about the state of vulnerability database, whether they are open or not. We'll be looking at how we search vulnerabilities and really how we should search for vulnerabilities, which should be really by package, and that's going to be the common theme. I will highlight how we can have a better approach, which is always going package first, and how and why we build vulnerable code, given the fact that there's a lot of already available vulnerability information in vulnerability database, be they open or closed. I'll show in more details our solution, vulnerable code, and how we went to create in specific elements to create this database, especially how we correlate and aggregate data from many different sources, and we do refinement of this data at multiple levels. Finally, I'll highlight some of the issues with existing vulnerability data that we collect and that we were able to uncover and we're trying to fix as part of this vulnerable code project, and some hints about our future plans. Let's start by looking a bit at the state of vulnerability database. It's not as great as it should be. We found instances of database that reference ghost packages, meaning when I say ghost, literally packages that don't exist anywhere. You could say it's a minor evil because, well, if they don't exist anywhere, it's not a big deal. You will never be affected by any of these vulnerabilities because there's no package. But it's really troubling to see that there's well-known professional commercial database that contains these references to non-existing packages. Or similar to this, database that make up vulnerable versions, literally either make up version that don't exist, so it's similar to the previous case, or they incorrectly report a package version as being vulnerable or non-vulnerable. Both cases are really problematic. The first case, if you report a vulnerable version that is not really vulnerable, you're creating what's called a false positive. And that means noise and a lot of work downstream for the security team because it's like crying wolf, literally. The second case is even worse because you're actually missing out a potentially vulnerable version. And that's what we call a false negative. In a way, it's even more dangerous because you may just ignore the fact that there's a vulnerability, even though there's really one that you should have been looking at. So that's what we called crying wolf, what I was saying again just a second ago. There's another case of crying wolf, which is what I would call improbable vulnerabilities, where say you have a package that depends on log4j. And instead of saying that log4j is vulnerable, the database will say the package that depends on log4j is vulnerable. And that's a real problem because you cannot do this kind of dependency tree reporting without bearing the risk of triggering a false positive. It's only if you use this exact version of the application configured in a certain way that you may have this dependency that may be vulnerable. It's not always all the time. So it has this quality of making the database of vulnerability look larger, but at the same time, it's less useful. And again, crying wolf means false positive. False positive means more work for non-serious issues. We have also found examples of version ranges which are completely contradicting, where a vulnerability says, vulnerability reports in database says, oh, all the versions before version 1, excluding the version after version 0, are vulnerable, which is self-contradicting. It says that they're vulnerable but not vulnerable. It's binary. You cannot have a bit of both, which is also a problem because basically you have an advisory and a report which cannot be exploited automatically. And there's also the case last of noisy and redundant duplicated vulnerabilities, where you may have a reference to a vulnerability which is inherited by a database from another database. And because of these, you end up having potential duplicates. Duplicate is the same problem because whenever you do a query, instead of having one result, one hit, you may have two. Two means investigating two things and checking whether they're the same. Again, requires more work for your security team and whoever is doing the review. It makes also automation much harder. In some cases, we have also vulnerabilities which are mapped to really hard to find CPEs. CPEs means common product enumeration, which is a standard from the NIST to identify products, software products, but also hardware products. And the problem is that they are just given name. And because you have a given name, you don't know exactly what it is unless you have the equivalent of a phone book to find where and who has this given name. And that makes you find a vulnerability, but if you cannot find what is the corresponding package, then you also have more work to process each of the vulnerabilities. There's a more pressing problem, which is what we call the telephone game. Basically, everyone in this trade that's building this security database, security vulnerability database, is trying to make up a bit of something by trying to improve the data. So they aggregate some data and they're trying to improve it. But they're improving things in a slightly different way. And many of them also are reusing each other's data. So I have examples of folks from GitHub that use data from GitLab and GitLab that use data from GitHub. So it becomes a bit circular in a way. And that's just an example of two mostly open data sources. But in making things slightly differently and relying on getting the data from others and applying automation on top, if you apply automation, machine learning, AI on top of bad data, the result is even worse. You know, the principle of saying garbage in, garbage out applies really very much there. And that's really the crux of a serious issue, which is everybody is basing their database on another database content. And you have subtle transformation and subtle damaging of the data at each step. And you end up, for instance, in the case of what is the range of vulnerable version of a given vulnerability for a package, you end up in some case having as many interpretations as there are database, even though there's really one ground truth, which was originally provided by the upstream project authors. And really, this turns into the Teflon game where progressively the signal quality and the data quality is degraded over time. We know that upstream has better data, and the real better source of vulnerabilities is upstream. And that's really where we want to go and what we're doing with VulnerableCode. So let's look a bit further at some of our other issues that are problematic in this space. Most of the database that exist today that report vulnerabilities, that is security bugs, about free and open source software, tools, and packages and libraries are mostly proprietary, and or if they're proprietary entirely, they are maintained privately behind closed door using proprietary tools, processes, and data. It's a real problem because we're talking about open code and open source code, and we really think that it's essential that open source tools and open source code depends and relies on open data and open source tools themselves. There's some improvements in that space though. GitHub release their data under an open source license, so does Google with the OWASP, and GitLab also, but with a 1 month delay, so you have slightly outdated data, which can be problematic when you have important vulnerability issues. Something also on the bright side is the support for package URL, which is a standard that started both in VulnerableCode and ScanCode Toolkit, and it's been widely adopted by several other players in the space, be they open source or not. And it's a way to identify a package in a concise, meaningful, and unambiguous way. It really promotes interoperability a lot. Google's OSV and the Open Source Security Foundation OSV at the Linux Foundation, Sonatype OSS Index are some of the examples and tools and databases that use package URLs. It's also used by CycloneDX and to a lesser extent by SPDX. Other bright spots, there's emerging common formats that promote interoperability. And it's really important because, again, there's a true long-running culture of having private and proprietary approaches. Being able to have common formats to exchange information about which package is vulnerable to what helps a lot. That's the OSSF OSV, which is primarily supported and sponsored by Google. The problem, though, is that having an open format is a good first step. It doesn't mean that you have common identifiers all the way to discuss about the same vulnerability all the time or the same package all the time. So there's a lot of efforts to do, but some bright spots. All right, now that we've looked a bit at the state, let's look at how we search vulnerabilities. The question we're trying to answer is very simple, is if you have a package foo version 1.0, is this vulnerable? That's as simple as that, so very basic. And we want to know all the vulnerabilities that are affecting this version, what are the severities, and potentially what is the version that has a fix, or is there a patch somewhere? How can I remediate around this? More rarely, it's interesting is, do I have, another question would be, do I have any package vulnerable to this vulnerability? It's a lesser concern because frankly, you are more interested about what you have and what are the packages you use than generally speaking vulnerabilities. You may at time hear in the news about these new security issues. So there could be a few rare cases where you may be interested to search for all the packages that exist in your code, in your products, and that's really important. That could be vulnerable to these vulnerabilities you've read about. But usually when that happens, probably too late, and it's better to be proactive and really look for packages to vulnerabilities first. That's what we call the package first approach. Again, find packages, look at vulnerabilities. And it's kind of weird, but the reality is that in many cases, existing databases have been structured such that you look up for vulnerabilities first, and you're a bit left on your own trying to figure out what is the package, library, system, app that is impacted, and how you could effectively find if you are using this in your product. So why vulnerable code? I guess the key issue has been accuracy and correctness. I mean, I've hinted to some of the issues we faced. Vulnerabilities are important, of course, but your code and the fact that you may use some code that is vulnerable is even more important than the vulnerabilities first. And the thing is that we couldn't find any free software vulnerability database that was both open, comprehensive, and would cover most ecosystems. When I say most package ecosystem, I mean system packages, such as like Debian packages, RPMs, as well as application packages like Python, NPM for JavaScript, Java, Maven, and the likes. And there was no database, and there's no database that's actually created by experts. And that's not only created by experts, but also validated, meaning that you have multiple sources that you can correlate, and you never take the data at face value, but you're trying to trust but verify. And that's really important here. As I said, we found a lot of issues with made up packages, made up package versions, incorrect vulnerable ranges. So this cross-validation is really essential to obtain better quality, more trusted data. And so we're trying to work slowly but surely towards correctness there. We think that it's more important to be correct and accurate than to be in a state where you may report false positive, which require more work. And they're really problematic because you overwhelm the security teams and the folks in charge of checking these vulnerabilities if you have these false positives. And false negatives, I said, they're even worse, because if you're missing out on a vulnerability, what's the purpose in the first place? Okay, so let's look at the vulnerable code solution. I suggest that we do a quick segue to look at the demonstration that will be a bit more lively. I'm looking here at Deja Code. And I've very simply searched for log4j, which is a Java package that does logging. So it's a technical library. It's widely used in most of the Java-based application system and tools. If you are using Java in your team, it's likely that you've been using log4j at some level. It's been subject to a few very high-profile security vulnerabilities in the last 6 to 8 months. And that becomes, therefore, a fairly easy target to look at. So we've been looking at just a bunch of packages to find the different versions of packages. There's a lot of versions, various packages. We have several thousand. I'm just going to take one of the standard ones here. And what I can see here very simply, there's lots of information about the origin, the license, and so on. But I'm just going to focus strictly on the vulnerabilities tab. And what I see here is that I have a vulnerability, which is about a SQL injection. SQL injection is a technique that can hijack data in the database and make it available to folks which were not authorized to create the database. So obviously it's a problem. And I can see a bunch of references here. The upstream reference here is the National Vulnerability Database, which has further additional details and information, including scores. It's reported as being critical here, and that's really important. We have this information available also in VulnerableCode. Another way to think of it is, well, here I was querying package out of the box in the abstract of anything. That's nice, but most of the time, I won't just query a package just for the sake of querying a package and looking for specific package version. What I'm going to have is a product or system or application. Here I have a sample one, which we call the Starship widget framework. And it has a set of packages and components. I can see the hierarchy, and I can see the inventory, and maybe check just for vulnerable packages. And voila, we have here the Maven package we're just looking at a second ago, which is reported as being vulnerable. I can then zoom on this, and again, that's the exact same thing I was looking at a second ago. So that's one way to look at the data. It's very powerful. Again, you don't have to look at everything everywhere. You can focus strictly on the subset of the code you use in your product. Another way to look at it is using a more streamlined and vulnerability-focused UI that we have in VulnerableCode. It's the same data. I'm just looking at the same package here that I was able to query. I can see, as you see, it's a bit more bare bone. I have several vulnerabilities. I can drill down on the vulnerability and eventually get access to the same data. Or I could look at the exact same data using the JSON API, where here I've queried my database using the package URL. And I can see all the vulnerabilities that are impacting this. I can see the score I was talking about. There's actually, that's another interesting thing. There's different ways to score and many actors that are providing scoring. We will eventually, as part of VulnerableCode, also provide our own scoring, which is going to be an aggregate score. As you can see here, you have, in this case, two references that come both from the NVD, and one which says 9.8, 9 which says 6.8, two different scoring systems. It's really important to be able to collect this information as reference, because here I have another one which comes with another value entirely and says it's critical. That gives you a bit an idea of the breadth and depth of the data we have on the one end. But on the other hand, remember, it was super easy for us to go from the inventory of our product to the fact there is vulnerability. Now, let's go back a bit on the solution. The first thing is to be able to find packages. And you can do that with tools like that report package URLs. We also support CP, which is this not exactly legacy, but historical approach to reference packages from the National Vulnerability Database. But we prefer package URLs because they're easier and they're very intuitive for software developers to understand. They map and match very well with the code you use, and that can be discovered by tools automatically. And they're not given names, they're names that you discover and that are derived from the actual content and package manifest that you find in the code base. Sorry, went out of presentation mode. So, okay, so some of the example tools here: ScanCode.io, ScanCode Toolkit, but also the open source review toolkit, Turn, the OWASP dependency track tool, and many more. Or you can use, of course, an SBOM. CycloneDX supports package URL as well as does SPDX. So that's the first step. The second step, you look up your package vulnerability in an open database. That's the vulnerable code. And you query by package URL. Again, I showed you earlier on here. This is the package URL information that's been streamlined. Here you can see how I query by package URL. As simple as that. That's the full API view. And in the end, both the data and the tools are free and open source software. Everything is available on VulnerableCode is available as an open source project on GitHub, and we are publishing in the upcoming release the seed data such that you can quickly also run VulnerableCode locally and privately. We are also making this data in this instance here, which is called public, but has not yet been publicized, shortly available now that we're reaching a very stable release. Important, open data, open source tools, in the end, I think are better for open source because otherwise it's just really doesn't make sense. Right now, we're spending a lot of time to review the data with tools. Eventually, we came to the conclusion that we need to review this data and have experts that understand the package and the vulnerabilities and the code, validate the data that we have aggregated and collected, just because there's too many inconsistencies, there's too many approximations, and in many cases, as I said earlier, many cases where people just transform the data and transform the data and transform the data, we need to be able to pinpoint this inaccuracy and validate that the data we have is correct. That's a lot of work, but I don't think there's much way around that in the end. Someone that says that you can only use automated tools today and just collect data in a fully automated way is probably not understanding fully the whole problem. So how do we go about creating this vulnerability database? First, as I said, we want to use the data from upstream. And that means going to the source, not to a second-hand database as much as possible. For instance, we go directly to the source for OpenSSL or Nginx. In some cases, just figuring out the syntax and the meaning of the vulnerability advisories published by the Nginx team required us to exchange emails for weeks at a time to understand what was the exact way to better understand their data. And that's really important. If you don't do that, I'm not sure many people do that, but if you don't do that, you won't get proper data in. And as I said, garbage in, garbage out. The second thing is recognize that not all data is equal, and there's better data source and there are lesser quality data source that we cannot trust the same way. And we've deployed the confidence system. That means literally say, hey, we've noticed that this data source is not relying on first-hand data and is transforming and enriching the data in a way that's been problematic in a couple of cases. And we would directively, manually apply a discount to data source until we can prove that the data is of quality, which means that eventually you end up having a dampening effect on vulnerability information which are made up. And that's really part of ensuring we can have better quality data in the end. So, of course, being able to aggregate and correlate many data source is important. You may have a vulnerability that exists upstream, say in OpenSSL, but then if you have a package that's on Red Hat or Debian, is this the same vulnerability? Is this the same package? If the same code, can you infer that the same vulnerability may apply to the same code? And so on. That's really important. And you can only do this if you aggregate all this data in one place and enable cross-checking and validating. And that's a way to daily discover, as I said, new relationships by mining this graph that eventually emerges of the relationship between packages and vulnerabilities. Remember, as I said earlier on, that it was problematic that some database provide the dependency tree information, and if there's a dependency down in the tree that's vulnerable to something, they report the package up in the tree as being vulnerable. We think it's a problem because the data ends up being very hard to process because you never know whether it's the parent or children that are vulnerable. Eventually, we end up having these capabilities also based on the graph we build in VulnerableCode, but without having the problem of always providing dependency information at the parent level. You want to keep dependency information at the child level. And eventually, again, I said, we need to review and curate. Tools, machine learning, artificial intelligence, very nice solution. In some cases, they can be super helpful to spot problems, to parse information and make sense of data. Unfortunately, they're not there to fix the problem yet. So we collect and parse many data source. We store these in a common data model. We cross-reference each of these to create a graph. And we use information from project-specific trackers. I mentioned OpenSSL, Nginx, but we're looking at several others. We also look at bug trackers, which are not security specific. And eventually, we'll be looking at commit logs and project change logs, where there are informations about security, which may, in some case, go unnoticed. And you want to know whether the specific information about security fix typically in a commit log or in change log. We look also at Linux distribution security trackers. They have historically been very active for a very long period of time. And they're interesting because they cover not only system packages, but they're also very active to report information about upstream packages. And finally, application package trackers plus aggregators. So several ecosystems have evolved to create, maintain, and provide data about their entire ecosystem in terms of vulnerabilities. It's a very important data source. By cross-referencing this, you may have a package that is a Rust package that we find vulnerable based on the application package tracker that can be confirmed, cross-validated based on bug trackers and commit log information for the same package, as well as CVRF or OVAL information found in the Linux distro package for that same package. And again, it's only by cross-referencing, cross-checking all this data together that you can get a better true picture. The way we work is by applying multi-level of data refinement. We start by taking essentially the raw data that comes from a data source in a staging area. And then we parse and make sense of it, and we convert that to a vulnerability and package data and how the two relates together, using something we call improvers. And we're keeping on the side things that we cannot improve on and make sense of, so they can be eventually investigated later on and used to resolve any issue. And then specific improvers can also mine the graph, cross-check with other data source, for instance, validate if a package really exists, or use the set of known packages to resolve the version ranges. If a vulnerability advisory says all the version of log4j between version 1.1 and 1.2.17 are vulnerable to CV 1.2.3. You need to know what are the versions between 1.1 and 1.2.17. You need to be able to compare other versions to know whether they're inside or outside the range. So there's a lot of technicalities and finicking inside to get these version ranges correct. All right, let's look a bit more now at some of the issues. Ghost packages and how we address some of them. So we talked about them, packages that don't exist anywhere. The solution we've implemented here is very simply have the ability to look up in the package registry and repositories upstream to verify that the package exists. If it doesn't exist, we're reporting an error so we can eventually decide whether the data is correct but missing in the upstream repository, or the data is incorrect, or the data is undetermined, not fully determined yet, and need maybe to be discounted in terms of confidence. So that's been the key thing. We talked about this problem also of lesser quality data. There's some vulnerability source eventually that cannot be fully trusted. It cannot be trusted is a hard word, but they have interesting and useful data, but they cannot be trusted blanket because they make inaccurate assertions. And so the way we address this issue is by storing a confidence level, meaning we know that this data is of lesser quality, and therefore we assign a number between 0 and 100, saying it's 80% confidence for this. And therefore we can distrust and discount, the data source we trust less. In some case, we have also processes and automated tools of our own that we're not 100% sure that they're always correct. We can even discount some of the automated assertion that we do. It's really interesting because, again, it's about being able to eliminate issues with false positives by including this notion of confidence. We discuss also incorrect and missing versions. The problem is that very often we have very ambiguous statements done by upstream. For instance, if you say on December 1st that all the versions of package log4j are vulnerable, the thing you really mean is all the versions you knew existed on December 1st were vulnerable in the past at this stage. 6 or 8 months later, the statement's probably no longer true and no longer applies to versions which have been released since. Some of them may still be vulnerable. The likeliness that there have been a new version published that's actually fixing the issue is, in most of the case, fairly high. And so we call this time travel, basically. We store this assertion. We know the date of publication of the advisory or the bug report or the vulnerability report. And we are going to resolve the range as it were in the past. That means we are going to look at, okay, on December 1st, what were the set of known package versions that's traveling back in time? And therefore, we know that in terms of confidence, what's sure was what existed at the time. And then we can expand this range and revalidate that at a later date, but taking into account the fact that there's new versions that were published since, that there could have been versions that fixed the issue that were also released since December 1st. And in all cases, if there's no such thing as fixing versions, we can apply a discount because the set of versions that have been released since the publication of the statement has changed. And therefore, new versions since short of any other information, we cannot have the same confidence that they are as valid as the one that existed at the time. It's weird, but unfortunately it happens more often than not. We have another issue which we alluded to, which is duplicated data. So some vulnerabilities are duplicate. It exists in all the database. The problem is that each time you have that, you end up having more work, noisy relationship, and lesser correlation abilities. Duplication in this case is never a good thing. And what we ended up doing is introducing a new ID. The first installments of VulnerableCode, we only used what's called the CV, which means common vulnerability enumeration or exposure. I'm not sure exactly what the acronym stands for. It's the ID given to a vulnerability by the NIST, National Vulnerability Database in the US. And we would create what's called a VulnerableCode ID if and only if there was none. It ended up being problematic in many cases because there are several cases where we ended up having incorrect aliases and difficulty to relate this to a CV. What we do today is that we always assign this vulnerability ID of ours, and we track aliases, including CV ID when available. And eventually, we want to ensure, as we grow and gain traction, that all the vulnerabilities we track have a CV ID. So we may at some point of time in the future become what's called a CV numbering authority, or CNA. So we can assign CV IDs and ensure that all the data we track are also available upstream. Again, the theme is here, want to ensure that we have open data. The importance of these aliases is that they are used to aggregate and correlate and relate and reconcile data together to a single vulnerability ID. And it means practically that we avoid a very large number of duplicates. There still can be some, and we have other processes that we're contemplating to help reduce these vulnerability duplications, but at least having a single ID goes a very long way. Other issues. There are many data sources. Sometimes they're unstructured, messy, and incomplete, redundant. Frankly, I understand much better why there's been commercial vendors that have been dominating this space, because it's complex. It's not easy. The way we're dealing with these many data sources, again, is by integrate all, if not most of them, and cross-checking between each of them. This way, we can validate the quality or the lack of information from one with another. Another topic is obsolete data. I don't care too much about vulnerabilities for Windows 95. I'm sure there is a use for it, but there's a bit of a bad attitude of many actors in the space, which is to say bigger is better. And they're trying to have always the largest, biggest database with the most entries. Frankly, more power to them, but we don't care too much about all vulnerabilities on Windows 95. And more is not always better. You need to be able to make a choice and focus on a single matter. Our primary focus, not exclusive, but our primary focus is open source software. And we find that commercial-only software, hardware, less interesting. And we are directively ignoring things which have 15 years old or they're part of a legacy that really doesn't bring anything except it brings volume. Volume brings complexity. Complexity is not a good thing to foster automation. Which leads to our future plans. We are all the time working on acquiring more primary data source, meaning going upstream at the source as much as possible. And I mentioned that several times. That's really essential. We are also trying to extend the breadth of the data. Something that's really useful is the commits that are fixing and or introducing the vulnerability. They're really useful because if you know the exact commit, that means the exact set of code that was either introducing a vulnerability or that is fixing a vulnerability, you can after that check whether you have the bug or the fix in the version of the code you have. You could also, in the future, using tools to validate if your usage of the code actually goes through the path of the code that is vulnerable. But that's another issue, which is it's one thing to say, oh, there's a vulnerability, but if you don't use the vulnerable code in question, there's no need to take any action right away. In the same line, so there's a tool called Yara, which is a rule tool to detect patterns in code, and enabled by commits and also some other techniques on binary data analysis, we plan to also, as much as possible, find ways to provide Yara rules together with vulnerabilities to allow better detection of vulnerable code, especially in the case when you don't use a full package, but you may use a subset of the code, or the code of a package may have been recompiled and bundled together. You may not always have directly a package information. We're looking forward to build a community peer creation system, including UI, much better than the UI we have currently, which is pretty bearable. And it's going to be really important because, again, we need the expert review. Unfortunately, the data that's out there doesn't make the cut to be readily usable for automation. We are applying also very selectively artificial intelligence and machine learning, but not so much for driving the process, but in many cases to spot issues and or parse and extract structured data out of unstructured data. And in many cases, a lot of heuristics go a very long way. We're also building a tool called VulnerableCode. There's a tool called VirusTotal. It's a company that was acquired by Google. And what VirusTotal does very simply is this. Oops, let me put that in another browser here. You can upload a file, and it's going to run all the different virus scanners that exist on the market and test whether there's a virus that is detected there. You have Symantec, Sophos, and so on and so on. The idea we have and the plan here, it's already on the way for VulnerableCode, is to use as an input a package identifier. We talked about package URL, and then queries all these different vulnerability database to validate if the package is known to be vulnerable in this database or that database, and so on. And of course, we hope that vulnerable code will come out on top, but in the end, we don't care as long as this helps promote better data and openness and better accessibility to vulnerability data for code. If you want to learn more about our project, I mean, you can try out VulnerableCode with a free DejaCode account or start. And feel free to register for upcoming webinars. You can read about the latest blog post of our VulnerableCode public release or download it. You can also check on GitHub and the NextB website for more information. We have a fairly extensive documentation there. And if you want to help, you can contribute code, time, documentation, or cash. And feel free to use these tools and specification that we publish to VulnerableCode, of course. We have several other tools on VulnerableCode, beyond VulnerableCode, on About Code, and including package URL. And we also have a chat channels on Gear. That's it. Thank you very much and have a wonderful day. I look forward to discuss more with you.